students. Today about peak reading AC voltmeter in that two types: series capacitor, peak voltmeter, and generator. Okay, and generating voltmeters. Okay. First, we shall discuss this one. Okay. In some occasions, the peak value of an AC waveform is more important. If you take any examples, any electronic devices also, peak value of an AC waveform is more important, because to obtain the maximum dielectric strength of an insulating solids or any etc. If you take any example, then waveform is not sinusoidal. RMS value of the voltage multiplied by square root of 2 is not correct. If for RMS value we will multiply the square root of 2, that is not correct. Okay, hence a separate peak value instrument is desirable in high voltage applications. Okay, for small voltage applications we can multiply into square root. Okay, square root of 2. For high voltage applications we need a peak value instrument. Series capacitor, peak voltmeter, that we call Chubb Fortescue. Okay, there is a small mistake, FRO. Okay, Fortescue method. This diagram, okay, this is a diagram for series This is a diagram for series capacitor, peak voltmeter. Okay, C is a capacitor, P is a protective device, D1 and D2 are diodes, and I is a indicating meter. In this, V of T is voltage waveform and IC of T is a capacitor current waveform. T is a period. Okay. When a capacitor is connected to a sinusoidal voltage source, okay, if capacitor is connected to a sinusoidal voltage source, the charging current I naught is equal to integration of the charging current I naught is equal to integration of 0 to t V into dt is equal to j omega CV, where V is the RMS value of the voltage and omega is the angular frequency. If off-wave rectifier is used, the arithmetic mean of the rectifier current is proportional to the peak value of the AC voltage. If we use capacitor is connected connected to sinusoidal voltage source, then charging current will be I naught is equal to what? Integration of 0 to t V into dt. Okay. If a off-wave rectifier is used, okay, if we use off-wave rectifier, then the arithmetic mean of the rectifier current is proportional to the peak value of the AC voltage. Okay, they are saying that it is proportional to the peak value of the AC voltage. Next, the DC meter reading is it is proportional to the peak value of the value Vm. Okay, here the DC meter reading is proportional to the peak value of the Vm. Vm is equal to 1 divided by 2 pi Fc, where I is the DC current read by the meter and C is the capacitance of the capacitor. This method is known as Chubb-Fortescue method for peak voltage measurement. Okay. The diode D1 is used to, in this diagram, okay, there are two diodes D1 and D2, okay. The diode D1 is used to rectify the AC current. Okay, the diode D1 is used to rectify the AC current in one off cycle, while D2 bypasses in the other off cycle. Okay, what does two diodes work? D1 will rectify the AC current. Okay, it will rectify in one off cycle, and while other diode will bypass in other half cycle. This arrangement is suitable for positive or negative half cycle, and it is valid only when both half cycles are symmetrical and equal. One thing you need to remember, D1 and D2 will work on, it will work both cycles, okay, positive and negative half cycle, and it is valid only when both half cycles are symmetrical and equal. This method is not suitable when the voltage waveform is not sinusoidal but contains more than one peak. Okay, you can see this diagram. Okay, voltage waveform with harmonic content showing false maxima. Okay, this what they like this it is there, right? The charging current through the capacitor. The charging current through the capacitor changes its polarity within one half cycle itself. The shaded areas, you can observe here, this is the shaded area. Okay, shaded area in this figure gives the reverse current in any one of the half cycles, and the charging current through the capacitor changes its polarity within one half cycle itself, and the shaded area gives the reverse current in any one of the half cycles, and the current within that period subtract from the net current. Okay, they are saying that the current within that period subtract from the net current. Okay, starting current, it will subtract from the net current. Next is, hence the reading of the meter will be less. Okay, hence the reading of the meter will be less, and it is proportional to Vm as the current flowing during the intervals T1 to T2. You can observe here, from T1 to T2 it is reduced. Okay. Next, the second order false maxima is easily spotted out by observing the waveform, the charging current on an oscilloscope. They are saying that the second order false maxima is easily spotted out by observing the waveform of the charging current. Okay, waveform of the charging current means this one. Okay, this one is the waveform of the charging current, and on an oscilloscope under normal conditions with AC testing. Under normal conditions with AC testing, such waveforms do not occur, and such do not give rise to errors. Okay, they do not give rise to errors. Under normal conditions, you will get sinusoidal waveforms, but pre-discharge current within the test circuits cause very short duration voltage drop, which may introduce errors. Here it is. Under normal conditions with AC testing, such waveforms do not occur, and such do not give rise to errors. But pre-discharge current, okay, pre-discharge currents within the test circuits cause very short duration voltage drop, which may introduce errors. This problem can also be overcome by using a resistance R, okay, in series with capacitor C, such that CR less than 1 divided by omega for 50 Hertz application. Okay, we can overcome by that by using what? Resistance in series with the capacitor. Okay, that condition is CR should be less than 1 divided by omega for 50 Hertz applications. The error due to the resistance is delta V divided by V is equal to V minus Vm divided by V is equal to open bracket 1 minus 1 divided by 1 plus omega square C square R square, where V is the actual value and Vm is a measured value. Okay. In determining the error, the actual value of the angular frequency, that is omega, has to be determined. Okay, the different sources that contribute to the error are the effective value of the capacitance being different from the measured value of C, and one thing is different sources that contribute to the error is first is C. Okay, next imperfect rectifiers, which allows small reverse currents, okay, and also rectifiers, and non-sinusoidal voltage waveforms with more than one peak or maxima per off cycle. Next, deviation of the frequency from that of the value used for calibration. Okay, these are the points which different sources that contribute to the error. Okay. Next, we shall go for the generating voltmeters. High voltage measuring devices. High voltage measuring devices will employ the generating principle when source loading is prohibited. They are saying that high voltage measuring devices employ generating principle when source loading is prohibited. Van de Graaff generator, that is a high voltage, that will produce a high voltage, right? When direct connection to the high voltage source is when direct connection to the high voltage source is to be avoided. Okay. A generating voltmeter is a variable capacitor. A generating voltmeter is a variable capacitor, electrostatic. It is an electrostatic voltage generator which generates current proportional to the applied external voltage. Voltage generator which generates current proportional to the applied external voltage. The device is driven by an external synchronous or constant speed, okay, constant speed motor, and does not absorb power or energy from the voltage measuring source. They are saying that this is just introduction for generating voltmeters. Okay. Van de Graaff generator we have used to generate high voltage, right? And they are saying that a generating voltmeter is a variable capacitor electrostatic voltage generator, and electrostatic voltage generator is also used to generate the high voltage which generates current proportional to the applied external voltage. The device is driven by an external synchronous, okay, external synchronous or constant speed motor, and does not absorb power or energy from the voltage measuring source. Principle of operation: the charge stored in a capacitor of a capacitance C is given by Q is equal to CV. If the capacitance of capacitor varies with time when connected to the source of voltage V, the current through the capacitor is equal to I is equal to dq divided by dt, V is equal to V dc divided by dt plus C dV divided by dt. Okay. This is capacitor varies with time when connected to the source of voltage VDC divided by dt and CdV divided by dt. For DC voltages, dV divided by dt is equal to 0. Hence, I is equal to dq divided by dt is equal to VDC divided by dt. If the capacitance C varies between the limits C0 to C0 plus Cm sinusoidally as C is equal to C0 plus Cm sin omega t, the current is I is equal to Im cos omega t. Im is equal to V Cm omega. Im is a peak value. Im is a peak value, okay, peak value of the current, and the RMS value of the current, IRMS, okay. IRMS is equal to V Cm omega divided by square root of 2, okay. For a constant angular frequency omega, the current is proportional to the applied voltage. The current is proportional to the applied voltage. The generated current is rectified and measured by a moving coil meter. The generated current is rectified and measured by a moving coil meter. Next, generating voltmeter can be used for AC voltage measurements also provided the angular frequency omega is the same or equal to of it is same or equal to of that of the supply frequency. They are saying that omega, okay. Generating voltmeter can be used for the voltage measurement. It can be used for the voltage measurement also provided the angular frequency omega is same or equal to of that of the supply frequency. A generating voltmeter with a rotating cylinder consists of two exciting field electrodes and a rotating two-pole armature driven by a synchronous motor at constant speed n. Okay, they are saying that a generating voltmeter with a rotating cylinder consists of a two exciting field electrodes. Okay, it has two exciting field electrodes and a rotating two-pole armature driven by a synchronous motor at constant speed n. The AC current flowing between the two armature is rectified by a commutator whose arithmetic mean may be calculated from I is equal to n divided by 30 delta CV, where delta CV is equal to C max minus C minimum. For symmetric voltage, C minimum is equal to 0 when the voltage is not symmetrical. One of the electrode is grounded and C minimum has a finite value. The factor of proportionality n divided by 30. Delta C is determined by calibration. Okay. The AC current flowing between the two halves of the armature is rectified by a commutator whose arithmetic mean may be calculated from I is equal to n divided by 30 delta CV, where delta CV is C max minus C minimum. For symmetric voltage, C minimum will be 0. When the voltage is not symmetrical, then one of the electrode is grounded and C minimum has a finite value. The factor of proportionality n divided by 30. Delta C is determined by the calibration. This is the diagram for the S3, S0, S1, S2. Okay, this is S3 HV electrode, S0 is a rotor and S1 is a fixed electrode and S2 is a fixed electrode. Okay, S3 is a HV electrode. Okay, S3 is a HV electrode, S0 is a rotor and S1, S2 are the fixed electrodes. Generating voltmeters employ rotating vans for variation of capacitance. This figure gives a schematic diagram of a generating voltmeter. The HV source is connected to a disc electrode S, which is kept at a fixed distance on the axis of other low voltage electrodes such as S0, S1 and S2. Okay, you can observe here they are saying that S3 is a HV electrode. Okay, HV source is connected to a disc electrode S. HV source is connected to a disc electrode S, which is kept at a fixed distance on the axis of the other low voltage electrodes S0, S1, S2. Okay, S0, S1, S2. These are connected for synchronous motor. You can observe here this. The rotor S0 is driven at a constant speed by a synchronous motor at a suitable speed, that is 1500 or 1800, 3000 or 3600 rpm. The rotor S0 is driven at a constant speed, okay, by using what? Synchronous motor, okay. At constant speed means the suitable speed is 1500, 1800, 3000 or 3600 rpm. The rotor vanes of S0 cause periodic change in capacitance between the insulated disc S2 and the HV electrode S3. The rotor vanes of S0 will cause a periodic change in capacitance between the insulated disc S2 and S3. Between S2 and S3. Okay. The shape and number of the vanes of S0 and S1 are so designed that they produce sinusoidal variation in the capacitance. The generated AC current through the resistance R is rectified and read by moving coil instrument. Okay, it is measured by moving coil. The resistance will rectify the resistance is rectified and read by moving coil instrument. An amplifier is needed if the shunt capacitance is large or longer. Leads are used for connection to rectifier and meter. Okay, the amplifier is needed for what? An amplifier is required. Okay, an amplifier is required for what? An amplifier is required shunt capacitance is large or longer. Leads are used for connection to rectifier and meter. Okay, the instrument is calibrated using a potential divider. The instrument is calibrated by using a potential divider or spear gap. The meter scale is linear and its range can be extended by extrapolation. Okay. The advantages of this generator voltmeter is no source loading by the meter. No source loading by the meter. Next, no direct connection to HV electrode. Scale is linear. Scale is linear and extension of range is easy. Okay, scale is linear and extension of range is easy. A very convenient instrument for electrostatic device such as Van de Graaff generator and particle accelerators. Limitations: they require calibration, careful construction is needed, and is a cumbersome instrument requiring an auxiliary drive, and disturbance in position and mounting of the electrodes make the calibration invalid. Okay, they require calibration, careful construction is needed, and is cumbersome instrument requiring an auxiliary drive, and disturbance in position and mounting of the electrodes make the calibration invalid. Okay, this is the small introduction about generating voltmeters. Okay, explain about generating voltmeters. You need to explain few sentences about generating voltmeters, and next you should write the principle of operation and diagram. Okay, advantages and limitations of generating voltmeter. Okay, in next class we shall read about high ohmic series resistance with microammeter. Okay.